Okay, so I'm very happy to have a lot of people with Gil today in order to speak about Azul and the new Git and usage of modern hardware. Gil is CTO of Azul. I think everybody here know who Gil is, and I'm very proud that he can come at the PerfUG for the 42 sessions. Just a few things. We have another session beginning of July before the summer, even if it's hot today. And just a few words for Octo. Octo is a sponsor for the room, for the beers, something to eat too, but a lot of beers. We have normally enough beers for everybody today, thanks to Octo. So thank you to the sponsor. We Octo and Bohemi and us are from Octo, and we are hiring. So if you are interested, don't hesitate to speak to us. And now I let the microphone to Gil for the sessions.
Okay, thank you. And we'll switch to video, which will hopefully still work. Let me move this around. Let's see. Just testing to see that I can stand here and talk to you, and the camera probably can see me okay over there. Good. Okay. There. Okay. Yes. Yeah. Everything works. Okay. So, hi everyone. It's such a nice, chilly, cool day in Paris, isn't it? You know. I've been very nervous about this presentation. That's why I'm sweating. But yeah, this is a new experience for me. 99 degrees Fahrenheit in Paris is a pretty high number. So I'm happy to be here. It's nice to see a group with performance-oriented people, especially in the field I like to talk about. I like in a lot of my talks to use this background slide as a little bit of a high-level philosophical note for engineers. Who here, well, I think you know what this is, but who here knows what this picture is? What is it of? So that is the CO2 scrubber in Apollo 13. This is the ultimate duct tape engineering. They literally found a way to take a square peg and put it in a round hole. And you can see that there. And they used duct tape to do it from hundreds of thousands of miles away to save the lives of astronauts, right? So engineers sitting at NASA on the ground sat there with all the stuff that's on the spaceship and figure out how to do that and tell people exactly what to do to get that happening. And the reason they had to do it, I'm not sure how many of you have seen the movie or read the book, or just some of you. But Apollo 13 had a malfunction, an accident, and went around the moon but couldn't land. And the problem was getting back alive. To do that, they had to physically move from the part of the spaceship that was meant to carry them back into the little part that was supposed to land on the moon, was only supposed to handle 2 people. And it needed to be there long enough so that the batteries that were left would be useful for actual getting the parachutes out and navigation and the rest for re-entry. The problem they had is the CO2 filters, the things that actually let them still have breathable air, were different for the lunar lander and for the main part of the ship. One of them was square and one of them was round. They were never meant to be interchanged. This was not a planned mission behavior. but they had to somehow have 3 people live in there and use the CO2 scrubbers. So they figured out how to do this. And whenever in engineering we get to do something like this, not necessarily save people's lives, but do something heroic, something that, everything is wrong, but we managed to save the day anyway. There's this amazing sense of pride, of achievement. And you should be feeling proud when that happens. But right along with it, you also have this immediate knowledge that most of your job is to make it so that isn't needed. Right? So the conclusion here is, from now on, we should make sure the CO2 scrubbers are the same. Right? That would make this unneeded, right? It's a simple thing that people didn't think of ahead of time, and had they thought about it, the heroics wouldn't be necessary. But when we do this, that's where we test our actual skills. And then our job is to not have to use those actual skills every day, because that's not how it's supposed to be. We'll get back to that a little later, perhaps. The subject we're going to talk about today is, I call it Java at speed. No problem. And primarily looking at how to get the most out of modern hardware, and how Java can or does or will get the most out of the modern hardware that we have. It's interesting to me that we haven't really paid that much attention in the last 8 or 10 years to the improvements in hardware that go beyond just more of the same. So improvements that are actually new capabilities, new instructions, new functionality that could be used more optimally in code. And we'll get into some details there. The high-level agenda is we're going to look at some introduction and motivation. We'll talk about some of the hardware trends of the last 8 to 10 years. We'll talk about some compiler things. I'll talk about how compilers do optimization, simple things, that simple optimizations that are easy to follow, hopefully, and understand. We'll then talk a little bit about micro-benchmarks, and mostly to see how scary it is that they don't measure what you think they measure. And then we'll get back to compilers to talk about some more cool compiler things that only things like JVMs or managed runtimes can actually do, only just-in-time can do, where static compilers can't do. We'll then talk about warm-up, why we have warm-up, because we'll have enough information to base that on. And finally, put it all together into what it all means to speed. I have to warn you, that's along the line, and especially towards the end, I will be bragging about what we do at Azul. We think we make the best JVM on earth. We think we do the right things to make Java go fast in all the ways going fast matters. And I'll explain that as I go. But this is not about Azul as a talk. It's about understanding these things. And I hope there will be either new learning for people who don't know some of these things, or even if you already know this, maybe this is a different way of thinking about it, or another way of looking at it. So I'll quickly say who I am. I assume most of you already know who I am. How many of you have seen me talk somewhere before, either on the internet or live? Okay, so good half of you or so. So I apologize, you're going to see the same picture again. I always use this slide. I'm the co-founder of Azul. I'm the CTO there. I've been working on garbage collection and many other things, but garbage collection for a while now. Here's a picture that shows that I actually work on garbage collection. This machine is a trash compactor. It's in my kitchen. The job of a trash compactor is to perform minor GC compactions during the week so that we only do the full GC once a week where we take the bag and go out. That's because we're lazy. I'm lazy. But that technique is actually very similar to how things in financial services work, for example. So there's a lot to learn from either way. Here, the compactor didn't work right. You can see that it had a fragmentation problem. You can see the little pieces coming out the back that were stuck in there and the mechanisms didn't work. So I had to open it up, defragmented it manually, fall back to a true full GC. And then I thought it would be funny to take a picture with the garbage collection book when I was doing it. Okay, so there's a cool picture. By the way, just a couple weeks ago, my trash compactor has started acting up again, so I'm going to refresh this picture soon. I just need to get ready, and I'm here right now. But this picture is from 2004, so I look a little younger, probably much thinner, and I thought it was funny all the way back then, right? So that means I've already worked enough in garbage collection to make bad jokes about them. I've also built lots of other things: virtual machines, physical machines, big subscriber management network things with millions of people running in them, and had to build an app server because people didn't have an app server yet, so we had to build our own. This is before WebLogic. And I even got to help design chips and instruction sets. I got people to put in an instruction in a RISC machine that we built. The instruction was focused on getting 64 bits into registers with fewer instructions. It's called get immediate long. Think about the initials for that. So I won't get to name an instruction after myself ever again. That's behind me, right? And at Azul we make JVMs. That's what we do. Another topic I talk about, we won't talk about it here, is response time measurement, latency measurement, how terrible the world we live in actually is and how scary it is. You can find material about that online. And like I said, that's not the subject for today. But I actually was very flattered that a few months ago there was a talk here at Devox France about something I built, HDR histogram, an entire talk about something I built, which I thought was really good, and it was in French that I don't understand. So, I watched it, but hopefully it said good things. But that's part of the subject I often dive into. Okay, speed. What is it good for? Absolutely nothing. Say it again. This is a joke about a song, right? But what is speed good for? It is important to think about what are we going to use the speed for? What do we mean by we're fast, right? So for example, are you fast all the time or only in between code changes? What if you change the code 70 times a day? That's sort of common today. So are you fast all the time, or does every time that you reload code mean that for the next 10, 20 minutes, all transactions are slow? Or maybe slow, right? Are you fast all the time, or even when load is high, even when the business needs you at the most critical time, or is it just when it's convenient? In financial services, are you fast when the market opens? Oh, that it's getting ahead of me for some reason. Yeah, are you fast when the market opens? Nothing's happening. Suddenly the market opens. There's a lot of volatility, a lot of traffic. There's a period of a few seconds or a couple minutes where some of our customers that are hedge funds say they make half their money in that 2 minutes. Because that's when opportunity is, that's where risk is, that's where you have to be fast or you don't want to play. Are you fast then, or do you need to not be in the market where everybody's playing? And then, are you reliably fast, or are you just fast for a little while, and then it's really bad? Right? These are all different questions about speed that are important to ask, because while we think that speed behaves like this, it doesn't. Speed is not a constant thing. In the Java world, and not just in Java, in most runtimes, most managed runtimes, most environments with JITs and garbage collectors and operating systems, this is how speed behaves over time. It changes. It changes from the beginning to later. It goes up and down in between. And even once you think it's stable, it's not actually stable. It's very stalled, jitter, pickup, whatever you want to call those things. So what's behind this? We're going to break this down to the pieces that make that speed behave like that. And the first one to understand is that when we run code in a JVM, we start with very slow interpreted code that we loaded from classes. We actually run that 1 byte code at a time with an interpreter. And the JVM sort of sees what code gets run a lot, and once it's run a lot, it pays attention to it and tries to make it go faster. So at first it's slow interpreted code, then we convert it with a very cheap compiler that very quickly converts this to machine code instead of bytecode at a time, but not very optimized. And the main role of that green layer is to collect profiling information so we can optimize. And after a while is actually 10,000 operations of doing that and collecting a profile for any piece of code, we will apply a highly optimizing compiler and convert the code to something that goes really fast, hopefully, and that's this blue code. So code moves from being primarily interpreted to a mix of interpreted and lightly compiled to primarily optimized over time. And that evolution changes the speed over time. If we look at this from a response time point of view, at the beginning, things take a long time for each operation because they're interpreted. Slowly, as we replace that with compiled code, it gets faster by a factor, but still much, much slower than it will eventually be. And after a bunch of learning and unlearning and stabilization, it will hopefully get to this everything is fast, or everything you actually do is fast, or almost everything you do is fast. That's the blue part. Now, these red spikes are those annoying other things that the JVM sometimes does. It will stop for no good reason, really no good reason, every once in a while to do things like garbage collection pauses and other things. And those are huge stalls that could be milliseconds, tens of milliseconds, seconds, sometimes more than that. And they vary by behavior and application, but they're there all the time. That's response time over time. But that's not speed. That's how much time it takes. If we want to think of this in terms of speed, we need to sort of do 1 over x on time. So that's how speed behaves over time on that same information. We start slow, and we get faster and faster. We start slow because it's all interpreted, and interpreted code is really slow. And then we convert to that green compiled stuff that's 3, 4, 5 times faster. Much better, but not nearly as optimized as what we can do with the highly optimized, speculative optimized stuff. And then over time, we'll convert to this. And even when we convert to this, every once in a while, we'll take a phrase, go to a 0 speed for a while, and then get back to running at speed. So even after we stabilize, we go from being fast to being 0 to being fast to being 0, with the transition being very abrupt. So that's how speed behaves over time. And you know, it'll keep going to the right here. Let's look a little bit at servers, modern servers, and talk about the trends there. That was a little bit background, a little introduction. Here are some servers. These are the actual model names, Intel code names for models for cores, the actual CPU chip that they come in, mostly for 2-socket configurations that I chose there, the introduction date of each of those. And then on the right, we have how many cores are in each chip. And here we have features. Every once in a while, new features are added. There's new instructions or new capabilities that might be interesting. We are right around here today. If you recently bought a server in the last year, or you're running on a cloud environment, you're probably running on one of those. If it's longer than 1 generation, 2 generations behind. But in reality, we're actually just now expanding here. For example, right now in the Google Cloud Engine, you can rent one of those. Even though it's not publicly announced, and Intel hasn't actually released the specs, you can actually run on it. And just pay 15% more to Google, and you can run on one of those. That's really cool. So we actually looked at what it looks like. But that's about to become available to everybody. And that thing has new features. So that gets interesting. Some more about trends here. Over time, and this has been going on for a really long time, these CPUs have gotten more and more capable at doing a very complicated juggling act. And the mental model that says the machine runs an instruction at a time, or maybe 2, or maybe 8, doesn't really work for thinking of how execution works. The right way to think about it is the CPU grabs an instruction, throws it up in the air. It does that with 200 of them at the same time. It waits for them to partly complete and throws them back up. It can keep 72 different loads up in the air and 56 different stores all at the same time with instructions not yet retired. And as they complete, it gets another one and throws it up in there again. And it does this completely out of order. It doesn't have to be the right order. It figures out the right order as it retires. It makes the right effects happen. That juggling act is so complicated, it's very hard for a human to keep a model in our brain of what's actually going on. Which is why if you look at machine code and think about it, oh, maybe I'll move this around a little bit, and maybe these two needs to be closer, or, oh, there's an unused slot here, put something, forget about it. The CPU is doing a lot more than you can ever think of. You're not going to improve it at all by reshifting the code around. You'll either make no difference, or worse, you will change the code to something it didn't expect, so it won't be able to juggle it as well. So the CPUs are really smart, and just need to remember their job is to fill their pipe and get as much work as they can get done moving forward as much as they can. Yeah?
Does the window mean that there can be instruction 1 and instruction 224? This is as much as far away as they can be reordered?
This is how many instructions, and it's actually not instructions, it's micro operations in these cases, but sometimes most instructions translate to 1 or 2 micro operations, can be kept going at the same time without being retired, without being completed. And why wouldn't they complete? Because, well, the machine only has 8 execution engines, only 8. When the instruction involves accessing memory, then it may take 300 cycles before we get that memory back, which would be a shame if we didn't throw some more instructions up in the air while this is going on, right? So the reason we throw them all up in the air is invariably there's this getting stuff from memory and storing things into memory that happen. And because memory is far away, hundreds of cycles away, we need to keep enough things in the air to keep that pipeline going. Otherwise, we would just stall and wait for 300 cycles doing nothing. Or feel very proud that we got 8 things done in 300 cycles. An in-order execution would just not get very far. So that's kind of these stats. We don't need to get into deep detail here. One of the things to look at is the trend. This keeps getting deeper and deeper, longer and longer. These are major generations. Every 2 models, Intel adds more features to the instruction, to the actual core, and everything gets deeper and more capable. So the CPUs are actually getting more done per cycle, or more able to keep the pipeline better and more full, which does mean more speed at the same frequency. Another view of a CPU, I'm not going to get into the total detail here, but here I'm going to use my magic pointer. Watch this. Voila. This is the instruction prefetch of getting instructions from memory in, decoding them and fetching them, scheduling them, figuring out branches, figuring out where we think things are going, and then actually executing them down at the bottom with execution units on the left and data access paths on the right. If we look at these parts, for example, this is the data access path from the CPU to the cache and memory across 2 key generations. On the right, we have Sandy Bridge. On the left, we have the newer Haswell architecture that also Broadwell shares. The key things to look at here is the data bus width from the CPU to the L1 cache is doubled inside from 16 bytes and twice times 16 bytes coming back to 32 bytes and twice times 32 bytes coming back. So 32 byte stores, 2 32 byte loads at this per cycle, which is twice as much bandwidth across 1 generation hop. In addition to that, there are more units to do that in. So we went from only 3 to 4. So more things could be put in flight at the same time. So if the L1 used to be a bottleneck, now we have twice the bandwidth to it, for example. And this goes all the way down. You can see that the L1 to L2 is doubled in width as well. And the CPU bandwidth to memory is also increased across those. Looking at the execution units, oldest Nehalem, then Sandy Bridge, then Haswell, things get better. we get more execution units from 6 concurrent things that could run per cycle to 8 all the way in Haswell. From only a few ports to more ports, and then the capability itself. For example, Nehalem was able to do 6 things at the same time, but only one of them could be a shift. And then we could do 2 shifts per cycle. We have vector operations that went from being able to do regular SIMD, SSC, MMX operations to the much more capable AVX operations, and then to the AVX2 operations in Broadwell. These are instructions that could do more things, and I'll give you examples of what that means, and they're wider too, on wider registers, more things at the same time. And in Haswell, we can actually do 2 of those per cycle. So each cycle, we can issue 2 vector operations. A little bit of detail on caches. For a very long time now, we've had a fairly constant L1 cache at 32K, both instruction and data, a 256K L2 for each core, and then a shared L3 that was about 2 to 2.5 megabytes of cache, but the more cores you had in a socket, the bigger the L3 cache was because it was shared. This is about to change. Like I said, Intel actually hasn't released the specs, so we don't really know, but we've kind of looked at what we can get our hands on. The L2 appears to have moved in Skylake to 4 times the size, 1 megabyte. The L3 has actually shrunk from 2 to 2.5 megabytes to 1 point something megabytes. But while this L3 used to be inclusive, meaning anything in L1 or L2 also has to be an L3, in Skylake it appears that L3 is not inclusive, it's exclusive. So you can have some stuff in L2, and that means that some other CPU could ask for it and communicate it through the L3, even though the L3 didn't have it. So we've kind of shifted capacity from the L3 into the L2s, not in an exactly interchangeable way, but it seems like there's a big shift underway in Skylake SP. And like I said, the actual specs are not released. So this is all deduction from what people have observed, but we'll find out when we actually get specs. Another very important caching technology that's new, sorry, not new, that caching technology has been around, but a huge step of improvement happened just in the last generation or 2, is TLBs, translation look-aside buffers. A TLB is a cache that the CPU keeps in order to translate virtual memory addresses to physical memory addresses. Every load and every store you do is in virtual space and has to be translated. Now, if the address you're looking at hits in this mapping cache, that basically maps pages of memory, then great, it's really fast. But if it misses, the CPU has to go and fill that cache, replace it with something else. That could include up to 4 or even 8 memory accesses if you're virtualized. And each one of those could be an L3 cache miss. So you could be looking at thousands of cycles to fill a miss. Missing in the TLB is often a hidden bottleneck for applications, especially in the instruction TLB. We often find code that grows and spreads and becomes big and is hot across a wide range, and we bottleneck on the TLB itself. And historically, the sizes were the L1 TLB. There's also an L1, L2 level. The L1 TLB was a few tens of entries that were able to be 4K or 2 megabyte in size, and there was backed by L2 TLB that's been growing in size over the several generations. But the L2 TLB was only able to handle 4 kilobyte mappings. 2 megabyte pages, these big fat pages we like to use, weren't backed in the L2 TLB at all. So the number of 2 megabyte mappings we could actually keep was only low tens, very low tens. That has changed dramatically with Haswell and Broadwell, where the L2 TLB can handle 1K or 1.5K 2 megabyte entries. A 2 megabyte entry is literally 512 times more memory per entry than a 4K entry, which means that we've grown tremendously in the amount of memory we can address at the same time without missing, and the amount of code we can address at the same time without missing. That step is huge, especially if you use 2 megabyte mappings, which we do. But also Linux tries to use it in some modes, and In other modes, you'll find you can run, say, hotspot with use huge TLBs and use it. There are various ways to use 2 megabyte mappings. They're much more beneficial in the later CPUs than they were before. Okay, a little bit about topology. We have all these cores. Usually they end up looking like this. We have a couple of sockets. Each one has a bunch of cores. Each one drives memory directly with channels. And between them, we have a high-speed connectivity for coherence and interconnect, so cores can go across it. That's roughly the topology. Within one of these chips, things generally look like this. We have these cores. They're sitting on a ring, a double ring, actually. Each core carries a slice of the L3 shared cache. That's the last level cache here. That's the L3. So if one of these cores needs to access the L3 cache and it's in a cache line or stripe that happens to be in right next to another core, it goes around the ring and then back. So the parts of the L3 are kind of spread around, not exactly the same distance, but they're striped by cache line. So it's not like you have some here and then some farther away. They're kind of not randomly striped, but striped. Right? And then we have memory down the bottom with multiple memory channels and I/O up the top. So this is how things used to look until fairly recently. We put more and more cores. We got a larger and larger ring, but we got to a point where there's too many cores to put on one ring. So things actually look more like this now. For the last couple of generations, we actually have 2 rings on the chip. Each one of them looks a lot like the cluster before. Each one of them drives memory. And there's this high-speed ring-to-ring interconnect on the chip that's really, really high speed. But it's still a potential bottleneck. It's extra latency. If the core on the right wants something from the core sort of on the right, that's one distance. If it needs to go all the way to the other ring, it needs to cross that interconnect. That's a potential bottleneck. It's extra latency. You can actually configure the chip today to run either in this mode where everything looks flat, this is all shared, one big cache, but some is close, some is a little farther, some is much farther. Or you can actually slice the chip in 2 and use what's called cluster on die, COD. It's configurable at the BIOS level, and say these are 2 separate NUMA nodes. Each is its own L3, it's not shared. Stay in your ring. Going to the other ring is like going to another chip, just a little faster. And you can control which one of those you use. That just adds more complications to which one is the right way to use it, and there's no good answer for which one is right for you, because you get much more symmetry, good isolation. People over there won't mess with this guy's cache if they thrash all over it, but you get half the cache size. So is that good or bad? That depends. Now, to add more complication, that's how a full chip looks. That's what the chip with all the cores in it looks. But you can buy all kinds of models of these chips. The one with all the cores is really expensive, right? So maybe we take 2 steps down. We don't want half the cores, but let's get, 20 cores, 18 cores, not 22, 24, 28. And then you end up buying something like that on the left. Now the cores are very different. You bought a ring and a half, right? They didn't take them off of one here and one there. You have a full ring, then you have part of a ring. And depending on how many more cores you bought, you'll have more or less. That gets even more complicated to think about. Again, you could just think of it as one flat thing, but these cores are not created equal. Depending on which one of them you land on, you'll have different behaviors. If you do cluster on die, oh boy, that's complicated. One of them has a bigger cache than the other. If you don't do cluster on die, if you land on this core, you might measure a different speed and different throughput than if you land on another core. So it's a complicated picture. And I don't have a good answer for how to think about it or what's right about it. Just be aware that it's complicated. The simplest way to think about it is if you don't want that noise, get the full cluster models, either a full 1 cluster or full 2 clusters. But in reality, most people end up somewhere in the middle because that's where the good price points are. So just be aware of the noise. Yeah. How is affinity handled?
Yeah, I mean, like, how does the L3 cache get filled by instructions on a particular core? Is it the cache local to that core? How do things get promoted?
So in the model where we're talking about inclusive L3s, which is everything that up to now, not including Skylake, and assuming not cluster on die, we didn't tell it to split this into 2 separate virtual chips. So one flat way, this is one L3. Think of it as this cache line is here. The next 64 bytes are there. The next 64 bytes are there. They stripe by cache line. They don't stripe by page. So the idea is it's spread
completely
evenly.
random.
Not random, but trying to be. The reason to understand that it's not random is we run into a lot of people that have nice, large, fixed-size data structures, and they only use the beginning of them. Buffers, packets, disk buffers, all kinds of interesting pulling of objects to avoid stuff, all kinds of off-heap things. So you say, okay, I'll take, this could be up to 4 kilobytes, up to 16 kilobytes, whatever it is. But most of the time, I only use the first 5 cache lines. That means you're only using 5 stripes. Right? You're hot on those stripes. And you can actually see those effects when you look at it, because there's, well, this is not random, it's striped, which means that if you have uneven use of cache lines within a page, or within a cycle, you know, there's only so many stripes, you may end up keeping some of the lines much hotter than others, some of the parts of it much hotter than others. Usually this is too much headache to think about, but having looked at profiles for cache misses, sometimes you see the bottlenecks happen around, well, you know, this is all, you know, the first few lines of a packet, and that's most of what this does, and they happen to hit set in the cache rather than spread around the cache. And by the way, set associativity has the same problem even without striping. When you're set associative, you can have a set that's very hot that self-evicts within the set, even though the other parts of the cache are not even touched and used. Okay, so these were all annoying, confusing hardware behaviors that I don't necessarily have a lot of tips for, but more keep it in mind. On the feature side, though, the features are very cool, and being able to use them and watching if they're used is becoming more and more important. So I'm going to actually jump into some machine code. For those of you who like machine code, this is going to be a lot of fun. For those of you who don't like it for some reason, then take a deep breath. It's only going to be about 5 or 7 minutes of this, and then we'll get back to the nicer stuff, okay? So here's some machine, well, that's not the machine code. I'm going to zoom into machine code. This is a feature of Zing where we actually run basically a browsable profiler on the JVM, and you can see the hot code, and you can click on one, and then you could actually get down to the actual machine instructions. There they are, very readable. Not really, right? Here's a whole bunch of machine code. Let's look at an actual mapping. Here's a Java method, a very simple one. It's a classic, let's sum up all the numbers in an array. Here's the machine code that a JIT compiler generates for that. Now, it's a little hard to figure out where that code is in this code. A really cool feature of ZVision, and the reason I always make my code hot to read it, so my technique for figuring out what the machine code is I'll take a piece of code, make it hot, run it in a hot loop, and then go use this thing, is we actually have a % time spent per instruction column. And that lets me focus and say, yeah, there's a lot of junk here, but that's the code I want to read. Clearly, right? That's the loop. That's where I'm spending time. So let's read that and understand how that's that loop. I don't need to read the rest. So that focus usually reduces it down to 5 or 10% of instructions I need to read. The actual code was twice as long as what I could fit there on the screen. So here we can actually look at the code and understand it. This, by the way, is on a Westmere CPU, a fairly old CPU, using SSE instructions. And this is an optimization or a translation that most JVMs will do already today. So what's going on here? That loop is exactly what vector instructions were built for. We're going to sum everything in an array. Vectors are good at this. So it uses vector instructions. the loop is actually unrolled to do 2 operations per loop. You have 2 move DQs, you have 2 PADs. Each one of those moves loads 128 bits, that's 4 integers, from some address into a register. So we loaded 256, 8 integers in those 2 instructions. Then we add those 2 registers into some accumulator registers, probably the 0 and 1. And then we do the loop iteration, add something to the loop and compare, right? So you can see that I'm assuming that RDI there is the 8, but basically we did 8 integers per cycle, so we're probably skipping by 8. Now once this is all done, we'll have the accumulation right here in these 2 registers, and something here probably adds those up when we get the total sum. I don't need to understand exactly what that does there. That's the hot loop. So that's really cool, nice. But that's with SSC and 128-bit registers. Let's take that exact same code and run it on a more modern CPU. So here's what it looks like on a Broadwell with our Falcon compiler that actually optimizes for AVX2 instructions. So what you see there, instead of doing 2 sets of operations per loop iteration, we actually do 4. And instead of doing, I'll go back one to show you instead of doing move and add, we use an AVX2 instruction that does a move and add in 1 operation. So that's VP add, right? Take that memory location, add it to that register. 1 instruction, not 2. And then we do 4 instructions per iteration. And each one of those is twice as wide, 256 bits instead of 128 bits. So 1 iteration around the loop does 32 integer adds instead of 8. Faster. And a Broadwell could do 2 of those per cycle, or a Westmere could do 1 of the other per cycle. So it's all nice, good. But this is classic vectorizable code. It's cool that we could do this, but how much of your code is actually that simple and vectorizable? Let's take another piece of code. Let's complicate life. Take this operation here. We're adding one array to another. We could do it with anything else. But instead of adding everything, which is what vectors were built to do, let's say that not quite everything. I need to check to see if I need to do this or not. So I put an if there. In this case, I'm saying let's add just the even numbers of B to A. Not all the numbers, only if they're even. And this could be as complicated as only the ones that are greater than 7 and less than 50 and whatever other conditions you want to have there. When you do that and you look at the generated code, and let's zoom in, this is what a classic traditional JIT will do on all CPUs, including modern Broadwells. Here are the 2 actual unrolled steps of the loop. So it unrolled this and did 2 iterations per loop. But you can see the operations here. It's a move of something into a register, a test of that against 1, that's the end in 1, a jump somewhere if it's not equal, that's the if, and then an add if it is equal, if it is equal, that's the add. We can see a mapping directly from each Java operation to a specific instruction here, no vectors. The CPU will actually have to do 1 step. It'll keep all of them up in the air and 8 of them at the same time in a cycle, but it will do 1 instruction per Java logical operation in there. The reason for this is we broke the vectorizing. We did something conditional iffy logic, right? In the real world ends up with a lot of these things that, our loops are not just do everything, just 0 everything, put 1s in everything, adds everything. Those are nice, but we often have, let's scan until we hit something. Or some other things like that. So that's the way things looked until recently. But now we have AVX2. And AVX2 actually added some really cool instruction capabilities. Specifically, it added masked vector operations. You can actually perform operations on a vector that are conditional on the values of another vector register. So do this only if this register has a 1 in it for that part of the location. And if you take a JIT optimizer that focuses on that, you get this code for that loop. So this is a little hard to read. What I'll do is I will highlight a stripe one logical stripe going through this. This has 4 interleaved stripes, so the loop is unrolled 4 times. The red highlights are steps in one stripe. So this is step-by-step logical that we can follow. What does this do? It'll load 256 bits from memory. That's probably the load of B, but 8 values of that. And you see how that's done 4 times, so it's 32 values per iteration. But in this stripe, it's 8. Then it'll AND that register with something. I'm going to assume that that something has all 1s in it, that the compiler somehow put all 1s in something to AND with. So that's a vector AND against 1. It will then compare the outcome of that, this YMM6, against something else. Probably all 0s. You look at the if, right? That's what it's doing. So now YMM6 is a vector register that has the result of the if, but for a vector. So it evaluated the if operation for all the integers, for all 8 integers at once, or if the stripes actually have the results of the if for 32 different integers at the same time in the stripes. Now gets the cool part. This V mask move is actually load something from memory into YMM10, but masked by this YMM6. This is the load of A, but only the values that correspond to the cells that this if is true for. We then do an add of the cells together, and we store back into A only the values that the if was true for, ignoring and not storing the parts that that if was false for. That's really cool. Okay, it's pretty cool to see this happen. Now, I've actually clocked how fast this loop goes on a 2.6 gigahertz Broadwell, and if you count how many integer adds it did, it does 2.8 billion integer adds per second. But if you actually think of how many logical operations were involved in each one of those, look at the loop. We have to, increment the count on the loop, test to see if we should be done with the loop, jump if we're not. That's 3 operations, right? And yeah, loop unrolling helps with this, but let's count them, right? Then we have to load the B of I, end it with 1, compare it with 0, and jump if it's not what we like. That's 7 already. And if we like it, then we have to load A, add B in A, and store back into A. That's 10 different steps to do one of the additions. So 2.8 billion adds per second is 28 billion logical operations involved in Java per second on a 2.6 gigahertz CPU. That's really cool. That's really fast. Right? And that is about, I believe it's about 4 to 8 times faster. I don't remember whether this is the one that it's 4 or 8 times than the previous loop could be, right? Because we use the right instructions. Now, by the way, I keep putting this little bird over there. That's a Falcon. That's our cool JIT compiler, is the thing that generates this code. And the really cool thing for us is Falcon is based on LVM. It's a new JIT compiler we just introduced in the last few months. And Azul didn't build this optimization. That's the coolest part. We didn't do this. We just pointed LVM at the code, and other people did the work for us already. Those other people are Intel, because they knew this is coming. You know? And this is a great example of the leverage we get from a community that actually gets LVM to compile and optimize things that we wouldn't bother with and Hotspot wouldn't bother with or hasn't yet bothered with. So we will today generate that code on Broadwell right now. And guess what? We tested this on a Skylake. We generate AVX512 instructions that are even twice as wide as that. So that loop doubles in speed on the new Skylakes. And while this is possible for any JIT to do, I'm not arguing feasibility or ability here, this is still not done in Hotspot, even though AVX2 has been in the market for 3 years. This is on the list of optimizations we could do but haven't gotten to yet, those, and we get to leverage a lot of other people's work. So thank you everybody who's contributed to LVM. We now get to show your work in Java. Okay, so that was cool machine instructions. Let's get back to speed. What does it mean to have a compiler that can generate even faster code with new instructions? Well, raise the speed. That's pretty simple, right? On this picture, we can go faster if we build a better or faster or JIT compiler or something that can use the new features of CPU in a better way. That's a trend. But not looking at a specific compiler, it's useful to look at what compilers actually do. The compilers are optimizing code. They take the code you wrote, the bytecodes that are there, and they translate it into machine instructions. We're done with machine instructions for now, by the way. Okay. But those were good examples of, different JITs will end up with different results, but it's allowed to take this code and make it that code to go fast. I'm going to go through very simple techniques of what compilers are allowed to do, and we'll build on them as we go. So let's start with simple compiler tricks. We're allowed to reorder the code that you write. If you wrote this code for whatever reason, the compiler is allowed to change the place in the order that this code is executed, as long as this doesn't change the meaning of what is done. So I'm not allowed to do this if I actually change dependent operation order. But that line could be reordered with no side effects, so it's okay. Compilers are allowed to do this. That's simple, probably easy to understand. We can also take code that is dead. Dead code means it doesn't have an observable side effect. So you don't know if it ran or not, so I don't have to run it. And I can kill it. That line doesn't affect the result. It's operating on local variables that nobody else will see, and it has no impact on what I return. So I don't actually have to do it. There's no way for you from the outside to check or prove whether or not I did this, so I won't do it. It's a valid optimization. Okay, we can take values and propagate them. So for example, here we have all these temporary variables we defined. And often people have this wish to write more efficient code. Well, I have all these steps, let's put them together. Well, the compiler will do this on its own. The lesson here is really write readable code, give your temporary variables logical, meaningful names so that next time you read the code, you'll know what it does. And it's okay to have these intermediate steps, because if they really are intermediate steps that you don't have to do, the compiler will actually take them away. There's no hit, no cost whatsoever to having good logical code with intermediate steps. I wish the IDEs recognized that fact better, because one thing that annoys me about IntelliJ, I like to return things that have a name. Like I'll compute something in a name because it explains what the math is, and then I'll return it. And for some reason, IntelliJ hates that I do that and puts yellow little warnings everywhere I do it because it's inefficient code. I don't know. But, that return will happen. Okay, now we can further simplify this math because, you see how there's a plus y and a minus y? Well, they'll cancel each other out, right? So the compiler is allowed to do that and say that's basically what the math is in that sequence. Those were all very simple transforms that every compiler and every language probably is able to do today. It's very static, simple optimization. And the lesson here is you don't have to write hand-optimized complicated code to get optimized code. The compiler's job is to actually do that for you, and it does it probably better than you can. So those were simple. Now let's do some more compiler tricks that are slightly up from there. We can take values and knowledge and propagate them through control flow to affect optimization. For example, here's a piece of code that has an if in it, and we might go left, we might go right. But we know that value is 5, so we know we're never going to do the first part of the if. So we know that bias is 1, and that's what we're going to return, so we're allowed to optimize it this way. It's a perfectly valid confirmation of that code. You don't have to do any of those instructions. The answer is 1. I should have put 42 in there, damn it. Yeah. So that's allowed. We can also take reads that you tell us to do. Like here I said read a.x, and then later I said read a.x again. I mean, I'm using a.x twice. Compiler is allowed to read it once and use it twice. So just because you said I want to do something with that field, that doesn't mean that that's what actually happens every time. We may just do it once and never read it again for that operation. Now that's a very important point to keep in mind, because here I just took 2 reads and I made them 1. Let me do a few more reads and made them 1. Let's say I loop as long as the flag is not set. I'm allowed to transform it to this. I can read the flag and then loop until my local variable is not set. And that's a provable infinite loop. It doesn't matter whether you set the flag or not. You're either going to enter the loop or never leave it. There's nothing in between. This is what the word volatile is for in Java. This is why it exists. If you don't declare that volatile, you deserve an infinite loop. Okay? Or if you wonder why sometimes this happens, this is why. But this is basically an optimization. It says, I've already read this, I don't need to read it again. It's allowed, unless you say don't, like using a volatile operation or some ordering that forces you to do this before that, this after that, and all those cool Java memory model logic things. Just like we're allowed to cache reads and eliminate them, we're allowed to take writes that are redundant and eliminate those too. Here I wrote 3 values to the same location. Now it's true that you could have come in the middle and seen one of those, but it's also true that it's possible for me to maybe have run so fast that you will never observe the other 2. Here's an important statement. Because it is possible for this to happen, the compiler is allowed to say it will always happen. Because you can't say it's wrong to do that. Maybe I did it really, really fast. You can't claim that you have to be able to observe the intermediate value. So here I did it really fast, so fast you can never see the middle values, right? It's a simple elimination because we can prove that we're going to override it, don't have to do it. Again, these were 3 writes down to 1. Let's do a few more writes down to 1. Here's a loop that writes 1,000,000 times. Here's 1. We know that the eventual value of this loop will be the top of the loop. We could just write that number down. We don't have to do the loop. Now we're starting to get interesting. We're eliminating loops, right? Okay. Inlining. Inlining in itself is an interesting, simple to understand optimization. For example, if we have a method, the method is final, so it can't be overwritten. We know that's the only implementation of that method, and somewhere somebody calls that method. We're allowed to inline it and basically take whatever we would have done there and put it in the code in the caller instead of calling the code. So in this simple case, we eliminated the overhead of reading, of calling and returning. And the cost of calling that method is exactly the same as the cost of accessing a field. So this is nice, good encapsulation. I don't have to make the field public. I can protect it with a getter. Good. But this is not the real power of inlining. It's not the removal of overhead. What inlining actually lets us do when we inline the code is to apply the other optimizations we talked about, and some others we might not have talked about, across that code. Let's take a concrete example. Here's a method. Now in this method, I don't know that value is 5, because it could be anything. It's an argument. I cannot optimize the logic in the if away. However, somebody is calling it with 5. If I inline the method at that site, I'm allowed to optimize away the entire method. So here I didn't remove the overhead of the call. The fact that I can inline it let me do value propagation, dead code removal, simplification, and all the rest, and we got really good code, right? So real value of inlining is that it expands the scope that other optimizations get to be applied to. And it's why you can write good modular object-oriented code rather than focus on doing really flat 10,000 line pieces of code because you're worried that maybe the compiler won't see it. It will. It will go very deep in inlining to search for it. Okay, so far we talked about fairly simple, common optimizations that pretty much all compilers, static or dynamic or JITs, will do. Let's take a little sidetrack to micro-benchmarking to see how fast code might run. And here's a piece of code. We looked at something like this before. I wrote a method. It counts to whatever I tell it to count to. I want to know how fast I count. So I'm going to time this. I'm going to look at how fast I do this, maybe run it 1,000,000 times, add up the numbers, deduce how fast I'm counting. If I run this, I'll find out that I'm counting really, really fast, as in this fast. That's a lot of zeros, too many zeros to figure out what magnitude we're talking about. It's impossibly fast. There's nothing that could do this on Earth, at least yet, right, at that speed. That basically says something is wrong here. That's an illogical number. It's not a valid measurement, probably. And by the way, if I ran it with different counts, I would probably find that they're all the same speed. It doesn't matter how much I tell it to count, I get the same speed or the same time. So what's going on here? Well, the compiler did something smart probably. So let's try to beat the compiler. That's a very simple loop. I'm just doing sum plus plus. Let's make it do math. Okay, let's have it compute something rather than just track the other thing. So we'll complicate it and do math, and we'll run it, and we'll find out that that's still impossibly fast. Why is it impossibly fast? That is dead code. Nothing you do in that loop, it doesn't matter what math you do there, will ever be observed by anyone. The compiler is allowed to say, I know I can not do this. You can't tell the difference. Except for speed, you can't tell the difference. And I like to make fast code. So basically, the fact that this has no side effects that anybody could see means I can just take it away. So what can I do to prevent that from happening? I could take that math and propagate it out. I could change this from a void method to a method that returns something I'm computing in a loop. So now I'll take that simple loop and I'll return it. Now there's a side effect. Whatever I do here will change the result. So I have to do the right thing. So I'll clock this, and it turns out that, no, it's still impossibly fast. The question was because of inlining? No. What was that? Yep. So if you look at this loop, at the end of the loop, sum will be equal to count. So the compilers are smart enough to know that, and they just return count. They don't have to compute it, right? Okay, so let's make it more complicated. Let's make it do that math. Now it's not as easy to say, I know what the result is at the end. And if you do this, is it better? Well, yes it is on some JIT compilers, until recently. So both Hotspot and our previous JIT compiler would end up saying, okay, I don't know how to do this. Let's just run the loop. And you will actually be timing the loop now. However, Falcon turns out knows that this is an arithmetic series, computes count times count minus 1 over 2, and doesn't do the loop. Again, we didn't build that optimization. Some clever guy in some academia wanted to beat some benchmark somebody else wrote, figured out there's an arithmetic loop in it, and figure out how to prove what the result would be. It's a side effect of us using other people's code. I don't really know what the true value of pre-computing arithmetic series is, except for beating benchmarks. I don't think this is something that valuable in the wild, but it's a good example of the compiler got faster, suddenly you're unable to measure it. This should be a warning to all of you. Just because you can measure speed now doesn't mean it's still measuring speed tomorrow. The next sub version of Hotspot might get some optimization that'll nullify our measurement technique, so you need to sanity check them. It should be tested, verified that the technique actually is real. Okay, maybe we can complicate it. That's an arithmetic series. Let's do it that way. Turns out that you could prove this is 0. Still can't beat it. Here's what I actually do today to beat all the JIT compilers I know of. It's complicated enough that they can't figure it out for some reason. Or nobody's bothered to say, I want to beat that, because they haven't seen enough of this code. Now that I'm showing you the talk, what do you want to bet that somebody's out there figuring out how to do this math, right? Because if you actually look at it, there's, the plus is only the only possible, there are only, 8 possible values of what we're adding here. You can actually look at the possible values of count and do an 8-way if and figure out what the sum would be, probably. It's just nobody's bothered to do that optimization because it would be silly, right? Just like the optimization for arithmetic series. Okay, so that right now beats all the current compilers. It'll actually count how fast I'm doing the loop. Okay, so that was the segue of micro-benchmarking is dangerous. Yeah, go ahead.
And about inlining, is it possible that the code in which you measure that doesn't use the loop ubench value?
Mm-hmm.
That's the compiler says, okay, there's a static main, but actually does nothing, so I just don't
That's
care.
a very good point. If the code that calls this a lot of times to do it, inline did it, could itself end up proving this away. But let's assume that in these techniques that didn't happen. And you're actually touching on a point I'm going to make in this slide. Microbenching is hard and tricky, and you may not be measuring what you think you're measuring. The trickiness can change over time. If you measured right today, that doesn't mean you're measuring right tomorrow. That's a very annoying feature of JIT compilers that improve. You need to sanity check everything. So check to see that the speed is possible and makes sense. Check to see that if you vary the work, the actual work appears to have changed. The number one sign of this isn't really doing any work is that the time is not dependent on what you give it. So things, for example, you give it twice the count, it looks like it ran twice as fast. That's not how real things work, so you weren't counting how fast it went. So that's the sanity check part. The best tip I can give you is use JMH. JMH is a micro-benchmarking toolkit. It's now part of OpenJDK. For older versions, you could just get it from Maven Central and find instruction how to use it. So use JMH, and use JMH, and use JMH. Please use JMH.
I have a question about with the new file column compiler, because JMH is basically built against the hotspot OC2 compiler and optimization. So he used some tricks to trick the compiler, the C2 compiler, but with Falcon, did you encounter some issues that the Falcon compiler is able to trick the trick of JMH?
So specifically, we don't know all the tricks, but the tricks appear to not be relying on tricks as much as using directives, and we do honor the directives. So there was a question before about inlining. One of the things that JMH will do very well for you is when you tell it to benchmark a method, it will prevent inlining of the method you're benchmarking by giving the compiler a directive that says do not inline that method. There's a way to do that, but it's very complicated and you have to put command line arguments with names of methods in them and classes. JMH does all that for you. It takes an annotation that says don't inline and it creates the right command line flags and runs stuff with it. We honor the same flags, therefore we're able to prevent inlining in the same way. Black holes seem to be working the same way. However, I told it to use JMH. That doesn't mean that you should believe the results. Every single benchmark I showed you so far was run with JMH. Okay? JMH can be fooled. I just fooled it, right? It did the right thing. It didn't let it get inline. But the compiler will do what the compiler will do to the code. And JMH cannot prevent the code from being optimized unless you tell it to, which usually you have no reason to. Now, JMH has nice, useful things like saying, put a black hole here. Make sure that there's a sim propagation that's better than what I just showed. But just because you use the framework to compile it, to run it, doesn't mean that it's disabling optimizations. Another thing JMH will do for you is it'll repeat measurements. It'll make sure things are warmed up. It'll run things more than once, measure the error in its measurements. So you don't fall into that trap of saying, I ran it and it was this speed, and I ran it and it was that speed, so this is faster than that one. And if you just ran it again, you would have gotten the reverse result because you just measured noise. For example, maybe you landed on that half node of the core that's on the wrong side of the L3, so that's why it's slower. So by measuring enough times, and you could tell it how many times to measure, the thing to keep in mind is when you want real measurement, you need to be patient. Tell JMH to run, go out to lunch, come back, see the results. Whenever you try to shortcut and say, well, just run a little, don't warm up that much, just run 3 forks, not 5, not 7, you're getting more noisy results. Okay, so that was micro benchmarking. Let's get back to compilers. That was just to scare you about micro benchmarks. So far we talked about the simple things all compilers will do, but what's special about JIT compilers is they can do things that are impossible to do without JITting. Now, the reason it's impossible to do is not because when you JIT you know better. It's because when you JIT, you have a fundamental ability to replace code on the fly. And if you can replace code on the fly, you can speculate some things that cannot be proven to be true and detect if they're not true and throw away the code and put other code in its place. That's something ahead of time compilers do not get to do. That's something static compilers don't get to do. They don't have a replace code method. That happens later. So those optimizations give us extra speed. And that extra speed turns out to be necessary in languages like Java, JavaScript, C#, Python. The more dynamic and cool you are, the more you need speculative optimizations. Okay? Dynamic dispatch is a great example of that. So let's look at some specific speculations. I'm not going to get to all of them, but I'll use some specific examples. One common one that JVMs do is to optimize away untaken paths, not by doing an if and presenting the code for what will happen there, but saying, I don't think that'll ever happen. I won't even generate code for it. I'll just say, throw away the code. This is just not right. So here's this example again, or something like it. What if we ran it 20,000 times and we never saw a value greater than 10? The compiler can do this. It will say, if the value is greater than 10, this is not good code. I can't run it. It's not correct. Do something else. Run the interpreter instead, please. But since I've thrown that away, I'm allowed to return 2. And there's a very common and valid question here that says, well, why can't I just do the if as well? And it's just as fast. It does the if, jump somewhere else, do the code there. And it's true that you could statically generate both sides. But now think of this with combinations and permutations and how big that other code becomes and how many ifs we might be doing and how fat this is. That's one thing. The other thing is the things that happen down that path may use values that happened before, and here I know they won't be used. So that allows me to optimize away things I can't validly optimize. If I don't know, I'll never go there. So down this path, down this part of the if, I can actually perform optimizations on previous things that I know, will not, that if never takes, right? So that's a simple optimization. It shortens things and it's done all over the place. You should be aware that the JVM will very often look at something you do and say, you never do that, let's not even generate code for it. It's not just methods, it's ifs and code that will do this. Implicit null checks. This is one of my favorite examples. You should know that every time you access a field in memory or something in an array, you're actually telling the JVM to do that code. You wrote that code, but you meant this code. It has to check whether or not the thing you're accessing is null. And if it is null, it needs to throw a null pointer exception, not do what you did, because what you did will crash. It has to do this. And if it actually did this, that would be really slow, because we access a lot of things in heaps and stuff, right? What the compilers, and most JVMs will do this today, what the compilers are doing when they're in the optimizing mode is they'll actually say, I don't want to do that if. I don't really think you're going to throw an exception. I dare you to throw an exception, right? And what it does is it generates just the code you have that might actually be using a null. But if it is using a null, we will get a segv, we will get a segmentation fault, a virtual memory address trap, and the JVM will catch it. When it catches it, it'll say, where was it? Oh, it's there. I know why it happened. I really should have checked for null. And I really should have thrown an exception, so do that in the signal handler. And now this code doesn't even have to think about it. Why is this an allowed optimization? Because the JVM can catch the signal. That's why you are allowed to do this. This is why you cannot do this in C, because you may catch the signal. Right? I'm not allowed to do an optimization that suddenly throws signals at you, right? That's not valid. But the JVM within its execution is allowed to say, I will always catch this, I will optimize this. Yeah?
Why field and array access and not method calls?
Why
not method calls as well? You mentioned field access.
Oh, field
when you call a method.
Oh, array calls will be the same. Yeah. It's all heap accesses. I just showed it on a field, but yeah, array at offset something is the same way for null pointer exceptions, because if the array is null
I'm not sure I understand. So is not the operating system supposed to throw the segmentation fault?
It does.
Or yeah. So
the
JVM catches it.
This, yeah, if you do this with a null, the operating system will throw segv. The JVM will catch it. And then it'll hide it from you, and it'll translate that segv to this code.
Okay.
Right? You won't know the difference. So it's valid, right? usually optimizations start with you won't know the difference, right? So now this is faster, but it's only faster if you're not throwing null pointer exceptions.
What's the ratio?
A lot. That's about 100,000 times more expensive than the if.
No, but more expensive than throwing the exception.
The throwing of the exception is not the cost. It's the catching of the segv. It's the context switch to a kernel stack. It's the context switch back. It's the walking of the stack. It's looking at all these side structures that are helping us do this. It's slow.
Total cost of handling an exception versus the total cost of handling an exception plus the handling the
I'm not sure about that ratio, but the important part is it's the cost of not handling. Yeah. So if it happens, it's extremely expensive. Because it's extremely expensive, the JVM doesn't want to keep doing it if you throw exceptions. So if you're frequently throwing null pointer exceptions, it'll say, I don't want to do this anymore. Throw away the code, put the if in. Frequently today means in that specific place, right? Frequently means 3 times. Okay? There's actually a settable somewhere for it, but it'll let you do it once, it'll let you do it times, third time. After the second time, it's replaced the code with an if. But only in places where you actually threw null pointer exceptions, and hopefully that's not on every field access you do and every array access. Hopefully it's never, but if you rarely do it, fine. And one request is, if you go and Google for Java performance tips, and you end up with this 1998 result that says, Java does these kind of things, and they do length check exceptions and all that, so how about if we run the loops faster by not checking? Don't do a for I equals that until length. Do I++ and let the array overflow exception happen, or array out of bounds exception happen, or run loops until the null check happens, or whatever that is. Don't check if it's null, just run them, even though they're null. The reason not to do that is because the JVMs will highly optimize code that doesn't throw exception, and it will really hurt code that does. There's a simple statement we like to use. Exceptions are exceptional. There's an assumption that exceptions are not your hot code. They're not the common way you do things. It's the way you deal with things that are rare. So the compiler says, if it's rare, I can make it slow. And it makes the fast case fast. This will recover from you doing it wrong, but you shouldn't have done it wrong to begin with, right? Basically, if you use a null pointer exception to exit a loop, you get slower code because you add if to the loop, where it wouldn't have happened. Right? Okay. Let's use a couple more powerful ones. Class hierarchy analysis. Class hierarchy analysis, let me go through the text so you could read it. JVM basically can see all the code that is currently in the JVM. It can't see the code you haven't yet loaded, but can look at this code and say, I don't know what the future will bring, but right now, in this universe, I see certain things that let me optimize. For example, it could look at things and say, there's only one implementer of this virtual method in the entire universe. So I can assume that anybody calling the virtual method is actually calling that one implementer. That's true until it stops being true. When it stops being true, for example, you load a class that has another implementer, the JVM will say, oops, there was an assumption here and it's no longer true. Go hunt down all the optimizations that depended on an assumption, kill them before loading the class. So the thing that you assumed is always true until it stops being true, but the code that assumes it will disappear before it stops being true. And that's a fundamental way that speculations are registered and acted on in the JVM. Class hierarchy analysis is a very good example of that in practice. Class hierarchy analysis is why you get to write clean or object-oriented code at speed. If it didn't actually exist, all the code you write probably would have looked different. Remember this inlining example I gave you? Well, I just dropped the final word. I explained before, with final I know I can inline this. The problem is final is ugly. Final breaks design. Final means nobody will ever get to extend my nice object-oriented base method. It gives you speed, but that's not worth it. When I know that the only animals in the world are dogs, cats, and birds, and so far dogs, cats, and birds still use that get color and didn't override it, I'm allowed to inline it to do this, based on that knowledge. So this is true as long as only one implementer exists, and class hierarchy analysis lets me prove that. And that is why your code is fast and clean. So look at what that code, what those optimizations mean. The fact that I can inline means I don't make the field public. Public fields are ugly. Hopefully you don't use them. They should be surrounded by getters and setters for encapsulation of actual behavior. Final methods are ugly unless you mean to use them. There are places where by design you need nobody to override your code because you logically need it to do a very specific thing. That's when you should use final. You should not use final to make things go fast. The good news is adding final to that line does not improve speed. If I take the final out, the JVM will always be able to prove the same thing because if it was final, you didn't override it. And if in the future you did want to override it, you'll probably be thankful that architecturally you didn't limit that. Okay? So what would make that break? Or what would make us throw away the code? Well, here's animal, and animals compute color this way. Imagine that we add a chameleon to the set of animals we know how to handle. And a chameleon computes the color based on the branch it sits on. So it's not a quality just of the animal. There's a way to figure out color. It'll probably override get color and do something else. If I load a chameleon into the JVM, this optimization is no longer valid. There are now two implementers. I don't know which one is called. I'm not allowed to inline the wrong one. So I have to throw away this code. I have to de-optimize it. Yeah. Yeah.
So what you just showed, I think it's called monomorphic call inlining. But so you just inline because there is a single implementation, but I think there are also specific implementation for the cases where there are two implementations or even three implementations. But I don't know, I don't understand how it can work because you can't just inline.
So this is not monomorphic inlining. The next slide is. So thanks for the question. This is not monomorphic. This is proving that a virtual method is actually static. Okay? It's not actually polymorphic. We've proved it by analyzing the universe and showing that there's only one implementer. However, what happens when I load a chameleon? I'm looking at this code. See, monomorphic site. Exactly what you asked about. Right? Now, there are multiple implementers in the known universe. I cannot prove which one this will be. However, the code here happens to be running inside the implementation of a dog kennel. And nobody has yet put a chameleon in dog kennels, so all the animals we've seen in this code have always been dogs. The site, there's a polymorphic call, it's a virtual call, but in practice, based on observation, and that's the difference for this, we have only ever seen one type for this. That's what we call a monomorphic call site. It's a type that could be virtual, but so far has only ever used one type. That type is a dog, so we're allowed to do this. We say, if this is not a dog, oops, this is bad code, throw it away. However, if I didn't throw it away, I know it's a dog. Do every optimization in the book, including inlining. So you will see monomorphic call sites that do just monomorphic dispatch, and you will see monomorphic inlining, which is what this is. So based on the knowledge of the type, knowing that this code wouldn't exist if this was the wrong type, I can inline. In terminology, we call this monomorphic. We call the opposite of this megamorphic. The reality, the computer science term is just polymorphic. There could be multiple implementers. Monomorphic could be multiple, but in practice only one. Megamorphic could be multiple and actually is multiple. In addition to monomorphic and polymorphic, we also have bimorphic and trimorphic, which is, I think, the things you asked. And you could probably make a quadmorphic, then I don't know what the right names are for the rest of them, but you know. We actually implement only three, like mono, bi, and tri. And it turns out that trimorphic inlining is very valuable in Spark. I don't know why, it is. Empirically, if you only do bimorphic, you lose optimizations on Spark. Not Spark the processor, Spark the platform. Yeah. So that's speculative optimization. And remember, that inlining may be a lot more powerful than just exposing the field. That could be something I could have propagated lots of cool optimizations into because it's a dog, but I couldn't validly optimize it otherwise. Okay, so this is good even if there are multiple conflicting implementers in the world, as long as that's true for the site I'm calling. So we did speculative things. There are many more speculative things, but you get the picture. You can read a lot of other material on what. Speculative optimization depends critically on one thing, the ability to take away the optimization. This is incorrect code. It must disappear if it's not correct. That is what we call de-optimization. Without the ability to de-optimize, we cannot speculatively optimize. The reason ahead of time compilers cannot produce speculative optimizations is the code they produce must be correct. It's not correct only if these are not dogs. It's correct. It has to handle all the cases, and that complicates matters and prevents optimizations. So de-optimization is a necessary evil to get this speed. You see this picture we showed before? And you would think you go from interpreted to slower to faster code, but look at all those spikes. Those are de-optimizations. We went and we optimized something, but we made the wrong assumption. We found out the hard way that the assumption was wrong. We de-optimized, went back to interpreter, relearned, reprofiled, then get the right blue code. All these spikes there are de-optimizations. De-optimizations are a temporary reversion of speed back and go forward, hopefully a temporary one. Right? However, these can happen at surprising times. So it's adaptive. It adapts to what you actually do, to the actual real world. And if you think microbenchmarking is the black art, welcome to the art of de-optimization or prevent de-optimization. Right? You don't want to de-optimize. How do I prevent the optimizations happening when I don't want them to happen? What can I do about it? Warming up the code so it's ready to run at full speed without the blips. How do I do it? And that's hard. Running the code long enough is not an answer. That's a sad truth, right? You can't just warm up the code and now it's good and ready. Because the optimizations can happen at any time. They can happen at 3 p.m. when the first occurrence of something we assume would not happen happens. Right? They de-optimize the first time something weird happens, and that could be because the world changed. Let's you often take code that seems to be warm up and you'll take a hit. Let's take an actual example. I'll use a financial services, easy to understand example. How many of you actually work in financial services? Okay, several of you. Oh, good. You've retired to the other world. Good. But financial services make for really good examples because we can easily apply really simple logic, much like compilers. You could say, we know that in financial services, people are greedy. That's their job, to be greedy. They're not working on the right thing if they're not applying greed. That's a different industry, right? So, you can, from that, figure out a lot of correct and right behaviors. So imagine, you're trading and the market opens and your job in the market is to beat other people in the market. Right? I mean, you're trying to be faster than they are and you want to win and they need to lose. That's how it works, right? So you need to be fast at the critical times, but unfortunately you're running some Java code, or fortunately you're running some Java code. And you really don't want to run interpreted during that critical time. You're just a sitting duck. People will steal all your money if you do this. So don't do this. How do I avoid running through my slow interpreted code at the most critical time of the day? I'll warm it up. What can I do? Well, I know roughly what the system's going to do. Let's do a lot of it. Train the thing, get all those JIT things out of the way, all the profiling things. So I'll have fast code when I start opening the market. And then we'll be ready. We're warmed up. We wait until all the compilations happen. We wait until all the deops die down. We can watch the compile log, see it's nice and quiet and stable. Now we're ready to put it in the market. You could do it an hour ahead of time, 10 minutes ahead of time, great. But usually people don't want to do 20,000 fake trades. Sorry, 20,000 real trades, because that's real money. And even if you could say, well, trade, oh, oops, sorry, I didn't mean that. Oops, sorry, I didn't mean that. The exchange might get angry at you and say, I'm not going to give you, I'm just going to listen to you if you keep canceling everything, right? That too, right? Although some of them let you do some things, but yeah, it depends on which. So you do fake things, and somewhere in your code you say, if this isn't real, don't really send it to some other place, do something else, right? But here's the thing, the JIT compilers are smart. They look at what you do and they assume that's what you're going to do. So you've done 20,000 fake trades, and what's the one thing you never did when you did a fake trade? You didn't actually send it to execution. The compiler says, I know, they never trade. Let's optimize for not trading. It's never ever happened, it probably won't happen. And then the very first time you trade, it says, oops, that's incorrect code. Let's throw it away, run interpret it for a while. We'll learn what the right thing is, right? And that's what really happens when you actually run that kind of mechanism. So if you want to look at it as a depiction, you went fast and boops, market open, you took a blip, and then you went fast again. Or specifically, we warmed up, we initialized, we optimized everything for this thing you do, and then we found out that's not what you really do, so we went back and boom. And it'll eventually be fast. That's what warm-up is. The optimization will often happen after you think you've warmed up. Because the real world is different than what you warm up with. So that's what we have. What do we want? We don't want slow trades. We don't want slow ops. That's what we actually want. It's important to note here that this focus that I'm talking about is not about starting up quickly. It's not about starting an ID and being able to press the buttons. It's okay if it takes a long time. I just don't want to be in a market when I'm slow. I'm okay preparing, saying, are you ready? Are you ready? Go. I just don't want to be slow when I'm actually doing things. It's a different motivation than let's start up quickly, in which case it's not about how fast you are, it's how quickly you got some speed. And those are trade-offs. So what can you do about it? One interesting technique is to log the actual optimizations you did. Not the result necessarily, but the inputs. We did this optimization with this profile and these assumptions. And then it turned out that that wasn't true, so we did these optimizations again with these options and these assumptions, and we dropped that assumption that caused us to de-optimize. So that's what happened. We can log all that, and then we can replay it. Next time we run the JVM, we say, well, yesterday we learned that that's what really happens. Let's start with that knowledge. Read all those in, prime all the profiles and counters. It's a little more complicated than go optimize everything. What we actually have is a very complicated dependency tree that says this method could optimize with all these things. However, you can't optimize it before all these things happen that it depends on. So don't until they happen. And at the point where they happen, go ahead. Those things are usually initialization. Initialization in Java has to happen in a certain semantic order. If you do wild random initialization, you'll get broken code very easily. So in effect, we have this log of all the things we want to do, and they're all waiting for things to happen. Every time something good happens, boom, a whole bunch of JIT compilations kick off. You get good optimized code, hopefully. Right? And those good optimized code is not just good optimized, it's good optimized with lessons learned. All the de-optimizations that happen will prevent us from performing optimizations that will fail those things again. So it's optimizing based on the eventual stable code that you hope you got to. You can also even build a workflow that says, am I ready? I started a JVM, I told it to start with yesterday's stuff. Is it done? Has everything that we did yesterday actually been applied? And you could actually see and say, well, wait, these 7 things, they happened yesterday, we still haven't optimized them. And the reason we haven't optimized is these 4 initializations haven't happened yet. You're not ready. Your job in a workflow like that is to get to a zero-length list. There's nothing that happened yesterday that you haven't applied, therefore you are ready. And you could do that by initializing things, force initializing things, but there are ways to get to a workflow that will say everything is done, or very close to it.
The feature specific to Azure?
Yes. So I'm describing what you could do, and then I'm saying, well, we did that, you know. So I'm describing what it could do, and basically you could take away the de-optimization, you can avoid that, you can warm up much more quickly without training. You don't have to run 10,000 operations, you did that yesterday. We know what the optimization needs to be, you just need to initialize some things and we'll do it. And back to this speed thing, Falcon raises the bar. We have a feature called Ready Now that does what I just said, and it brings that to the left and early. Right? Skip all that, go straight to what we know is the right thing. And do it very early in the run, hopefully before you even start trading. Now, there is a storm of compilation effort that happens. This doesn't record output of compilation, it records inputs. So we'll just storm in there and optimize everything we can based on a good, stable profile. And it might take a few minutes. So do it a few minutes early. That's the way to treat market opens and such. Unfortunately, there are some things that are more complicated than market open and hot code. For example, algo trading is often about watching things at millions of things a second, but only doing things 300 times a day. And that might be rare enough that even at the end of the day, we don't know what the right profile is. And then we don't really have an answer, not really, except that you can put compiler directives and try and direct it to do the right thing or warm it up in some other way. Because if you haven't experienced the real world in the log, that's just as bad as today. So just keep in mind that it's hard to get to perfect when the thing you're trying to be fast on only happens 3 times. Because we don't know and you don't know what it should actually do because it hasn't happened.
With Ready Now enabled, do you de-optimize if needed or not?
I'm not sure I understand.
I mean, you have Ready Now, you have a fast warm-up, everything is pre-computed, the optimization.
Mm-hmm.
But if it happens that you made false assumptions or there is clearly something new happening, do you de-optimize or not?
Yes, so if Ready Now, if you use Ready Now, you get the eventual compiled code optimized like yesterday. But if something new happens that didn't happen yesterday and it validates some assumptions, we'll de-optimize just like anything else. It's not hard-coded. We can still de-optimize, we can still adapt, we can still rejit. We just fast forward to the stable of whatever log you give us. And that could be yesterday, it could be the golden log you trained with, it could be last week. People do all kinds of interesting variations of this. An interesting other thing is people evolve their code. You know, when you changed your code, well, that optimization for that code is just not valid. We check some code. But in the universe of what you do, changing one piece of code doesn't necessarily throw away that much of the optimizations. Everything that didn't change, everything that doesn't involve the code you changed will stay. But the new code needs to learn. And that is a common thing that people will evolve their code over time, and that's where sometimes they'll retrain every day and use yesterday's stuff. Sometimes they'll create a golden master every month or every week, and basically understand that everything that changed in that week will be different, but they don't want to evolve during the week because they change so rapidly. They don't want to use yesterday's. They'd rather use a week ago than yesterday. Yesterday was a mistake. Let's not use that one. Let's use a week ago, right? Because a lot of times you're exploring in the world when you do this. Okay. So I did a little bit of bragging here and there. I showed you we have a great JIT compiler. Other people could have one too, but ours is better. And I showed you that you could do this, but we did, and other people haven't. Now comes the real bragging, you know. What's missing in this picture? You still slow down to 0 every once in a while, right? That's what the collector is here to do. The C4 collector is basically about taking away the big bad pauses and making them tiny little pauses you can't measure very well because there are bigger noises in the world. and they're very rare. We like to say that it eliminates garbage collection as an enterprise application concern. And we do mean that. Unless you're in the low latency world and you're talking about tens of microseconds and it bothers you when something takes 400 microseconds, you will not be able to tell the difference. So most of that universe, it's done, it's gone. In low latency, we need to be a little more specific. We do pause much more rarely and much more shortly, but it's important to understand that things happen. The impact of the collector looks something like this. You have an application with noise and blips and glitches, and then you run it on Zing, and it's much, much better. It still has a few blips because the application has blips, but those are not the JVM blipping. That's you or something else. And which application it is doesn't actually matter. The way to know that the problem on the left was GC is you ran it on Zing and the problem went away. So it was GC. Right? Or it was the optimization. Right? It's something that blips. Another side effect of solving this problem beyond just taking the blips away is to help with tuning. And when we say help with tuning is, let's take it away. Tuning for GC often looks like this. Anybody here ever use any of these flags? Yeah, a bunch of you, okay. But maybe use these flags instead. They're different. See, the number here and the number here are not the same number. Which one is right? Well, it depends on who you are, what your code is, whether this is Tuesday or Thursday. There are right numbers and there are wrong numbers. That's the problem with tuning. It's sensitive. Here's a lot of settings. Here are some more settings you can pick from. Every one of these is a GC flag. And the problem with tuning is that you're chasing a very sensitive, delicate thing and keep changing it. Every time you change your code, every time the data behavior changes, every time the world changes, your tuning may not be applicable. It's sensitive. There's so many things that need to be right. Our approach to tuning is to say, let's throw all this away. I mean the vast majority of settings for garbage collection are intended to take a bad thing and push it to the future. If we make the bad thing not bad, we no longer need to push it to the future. And all the flags that are involved with how we push it to the future go away. Tuning Zing usually starts with a large heap, whatever your machine handles, but you don't need a large heap. You then squeeze it down, and you squeeze it down, and you squeeze it down, and you find out how much heap you actually need. The way you find out how much heap you actually need is you squeeze it down so much that it doesn't work right, therefore you needed more. Right? That's how we find out. We twist it until it breaks, and then you just double or triple it, and you're done tuning. Rather than looking for this optimum tuning thing, you're really looking at stable, 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 oops. So let's stay away from here, stay here. Be in the insensitive part. And this really is an elimination of sensitivity. The machine is not complicated and smart and doesn't try to figure out what you're doing and get the right setting for 100 different settings for it. It just doesn't need the settings. The machine is simple. It does the same thing over and over again. It doesn't do rare things. It doesn't push things to late at night or next hour if it can. It's just simple, predictable, do everything all the time. To give you a feel for what we mean by that, when you run on Zing, unless you're idle, we will probably run an old gen every 10 minutes for fun. Why? Because we strongly believe in not running for a long time with behaviors that will happen in the future rarely. It's good that when you're idle, we won't do this. Our actual rule is, if we haven't done an old gen in 10 minutes, the next new gen will also do an old gen. If you're not kicking off new gens, you're idle or really slow, so okay. But if you're doing a new gen and it's been 10 minutes since an old gen, let's do one too. It doesn't hurt that much. It's just concurrent stuff. We spend a few more cycles on it. It doesn't slow you down or stall you. And when we say it doesn't slow you down and stall you, here are all the stalls. We actually log them. We try to do this honestly. And we think we are. This is Cassandra, not a low latency system. It's running on a modern Broadwell CPU, and they're nice and fast. And these are every pause in the system over about 3 hours of run, under full benchmark load. That line is the 1 millisecond pause line. When I say that it's hard to tell, then we pause. Most of the OS artifacts are above these numbers. So there's noise bigger than us And I can keep making this better and bigger, like better and better, and it'll be hard to prove it is because the other noise is bigger than us and more frequent than us. This is 3 hours. There's a lot more noise that happened in that 3 hours that is not pauses for the JVM. Now, that's cool. We clean up the glitches. We get the smoothness, but you also get to carry more load because of it. And you don't get to carry more load because we made things faster. Yes, we are sometimes faster. We have Falcon. But we get to carry more load because it's safe to carry more load. We're reliable at higher speeds. We don't necessarily crash into poles when you run fast. Or there's a higher speed at which this won't happen. A way to depict that, or to demonstrate that simply with the real-world example is to use a real-world example. And I like to warn here that you will not necessarily get this much benefit. Maybe your benefit will be half of this or a quarter of this, and that would still be amazing. But let's take a real-world example. Improve Digital, one of our customers, does video advertising. They monetize videos with ads. In order to do that, there's a whole bunch of bidding and matching and stuff I don't understand that's going on. It looks a lot like trading, but it's not regulated, right? So, I don't know why they don't call it. I mean, it's betting. It's just like trading, right? You're betting and just not regulated. Inside their implementation, they have a Cassandra cluster that is critical. The Cassandra cluster characteristics you can see here. It's got 80% writes, 20% reads. They actually clocked this around clusters this size, but the real question is how many nodes do I need in my cluster to carry a certain load? This is their SLA. If things gets worse than this, then angry people call you. And they might move to other vendors, and maybe your boss will not give you your bonus, whatever that is, right? This is the definition of that line between okay and not okay. They've chosen it. By the way, these are only reads. They don't care about write performance, just reads. Writes are, not critical. And normally, this is Cassandra. It answers in a lot less than a millisecond, but every once in a while, it'll take longer. So they're okay with it taking longer, just not that much longer. By the way, they wanted 5 nines at 100 millisecond, but it turned out that it's really hard to get 5 nines at 100 millisecond on AWS, even if you're idle. So they kind of lowered their standards a little bit. Now, what they did is they ran load and pushed and pushed and pushed until this was no longer true. The SLA broke. And when they did that with Hotspot, with G1, with this Cassandra cluster, this is after they spent a bunch of time optimizing it and getting G1 right and getting Cassandra to do the right things. They found that they're able to move 4K transactions per second through this size cluster. Therefore, they know, per node how much they can handle, per cluster what they can handle. And above that, things worked. They just failed the SLA. They can actually drive about 50K through the cluster, but not with an SLA. They clocked it in Zing, and exactly the same thing was able to carry 21K transactions per second before it cracked. And we didn't go to 50. Both of us could do about 50. We're actually a little faster. But it doesn't matter. The only thing that matters is how much you could do with an SLA. And that's more than a 5x ratio of how much you could do with an AWS instance. That's a pretty big thing. The reason is not that we run faster code. That's only worth about 8% in Cassandra. The reason is that we don't glitch, and therefore you don't need to add machines because of glitches. Or we glitch only at higher rates. At some point, you start queuing up and having other bad effects. So that's the real world effect. People might measure it with percentiles. You might monitor the percentiles and see that Zing makes things look better. But one of my favorite ways of actually looking at results is to look at the things you should be monitoring, not academic percentiles of what things might have been and how does that affect my business. Let's look at pain. How many times did we time out? What percentage of my operations actually succeed? This is an actual monitoring from an actual customer that I can't name. What you're looking at is a multi-day load. This is a week. These green things are 1-day patterns. And those 2 over there are probably the weekend because they're different than the other 5. I don't really know what it is. I'm just deducing. So those are how many total operations were done on this service. The service is a microservice that includes Cassandra. It's being watched from Hystrix with a circuit breaker, and these are the numbers, right? The orange line is the success rate of operations on this service. It's not as bad as it looks. The bottom of the x-axis is 98%, and it goes, so this covers from 98% to 100% success, the top 2% of success. But you can see how success moves up and down. Let's use my clever, actually let's zoom, there we go. I really like this thing, it's just, I gotta play with it, right? So you can see that at low load, when the green is low, the success rate is high. And at higher loads, the success rates are lower. You can also see that the success rates degrade over the day. That's actually very typical of systems that accumulate, you know, the work they do causes more and more problems down the line. Garbage collection looks like that. S-stable compaction looks like that. All kinds of interesting things that are, we're running really fast and we'll pay for it later. Eventually you start paying for it, right? So success rate tracks that. And I don't really know what the mechanism that leads to that is. I don't really care. What do I care about? I care about this side. You roll the cluster on one node at a time to Zing. It takes about 10 minutes and the success rate goes high. That's not 100%. It's just 99.99%. There's still timeouts and glitches. Cassandra has its own reasons for doing that sometimes. But you can see how dramatic the change is. And you can also see that we are handling the highest load at a higher success rate than the lowest load before. I can't deduce from this how much more I can push Zing to. I just know which side of the line we're on. Zing is happy, you can probably give it more. That's unhappy, you probably need bigger clusters. But operationally, I like to look at that. Now bringing it back to speed and doing the last bragging slide, that's that missing piece, that's what C4 does. And you can think of what Zing does to speed as those three things. We start fast, that's ready now. We go fast, that's what our compilers and JIT optimization is all about, and we keep making it better. And we stay fast, that's what the collector is doing, and that's what avoiding the optimization does. And that's what Zing is about. So Zing is about speed at Java, but hopefully you learned other things here too. So I apologize for the advertising part of this. I can't help it, but hopefully it's worth it. Okay, so with that, let's see what kind of questions are still left. Including the this can't be right or you know, or any annoyances you have. But what questions does this raise for you guys? Okay, thank you. Wow. Oh, there. Good. I didn't tire you all away.
When do you open source Zing?
When do we open source Zing? Well, the entire product it's hard to answer. It's, you know, we're a business. We need to make money. We haven't figured out how to make money by giving Zing away for free to everybody, and hoping that they call us. We're hoping to be able to do that. Maybe someday we will. But, and that's an important but, there are big portions of Zing and work that we have done that we have open source. For example, we just built Falcon. Falcon is an LVM-based compiler, JIT compiler, that we integrated with Hotspot. The LVM part of this is not Hotspot, it's LVM. And we had to do a lot to LVM over the last 3 years to make LVM able to handle things like speculative optimizations that we talked about today, de-optimization, safe points for garbage collection without losing all the optimization it knows how to do. There are a lot of things that we're missing in LVM. We've open source and upstream all of that. The upstream LVM is able to do the things we do. For other runtimes even. So the people building, you know, other runtimes using LVM get to benefit from all the optimization work that we did. And if somebody else wants to take LVM and attach it to a JVM, they can too. So we open source work that we can, or that we benefit from this because we like to be in sync with the upstream LVM stuff. We get, when they improve, we get the improvements, and to do that, we need to not diverge much. So we avoid forking that. You can also look at work we do with our OpenJDK. OpenJDK is usually focused on future, right? Java 9, Java 10, etc. So we have contributed work into OpenJDK, and we actually have a product line called Zulu that's purely OpenJDK without some of these enhancements. But there, we'll work on future features and push them. I'm actually really proud that I managed to get a feature into Java 9. It's the simplest possible feature you could ever add to Java. That was actually on purpose. I managed to add one method to Java 9, and the method is allowed to do absolutely nothing. You can't do less than that, right? Well, you could add comments and do nothing else, but you know. But that method is actually an on-spin wait method that helps spinning threads spin. They don't spin faster, they wake up from spins faster. It improves the reaction time of spinning threads. And you guys could all use it. You know, you can actually put on, how many of you actually perform spinning things, like you actually burn CPU spinning? So on-spin wait is built for you. It's the equivalent of a pause instruction that everybody uses in all other languages except for Java. Now you have one that effectively makes the JVM do that, and Java 9 does it. Zing also does the same on Java 8 and Java 7 and Java 6, but Java 9 does it, right? That's a good example of us taking something we want to do and pushing it upstream and hoping that people can benefit even before. The interesting thing is, even if you're not using on-spin wait, look under the hood at the actual JDK library, specifically at Java Util Concurrent. That's this one method I made that's used all over the place, right? Doug Lee uses it everywhere because all his backing off spinning and all the locks are now doing on-spin wait, so it's kind of nice. So, you know, that's work we do that we think is helping the rest of the community, but are we currently open sourcing everything? No. Yeah. I'll point out that very few other companies do either. Even Red Hat doesn't. Yeah.
Another question. Today, are you mainly working on improving the speed of the JVM or improving the regularity of the JVM, or the regularity of the throughput? What is the main issue today?
So the speed or the regularity. One of the reasons I kind of put this picture together is to answer that question without having to choose. Those are two different aspects of speed. So there's this speed and there's this speed. They're both speed. And there's also that part of speed. So we look at it really that way. We want to be flat, always the same. We're not really that. Nothing is really that, right? There's noise, but we think our noise is a lot less than others. We aim to get to the speed really quickly and stay at that speed consistently without the optimizations and pauses and other things glitching us. We're not perfect. We will stop for 400 microseconds sometimes, and you will still de-optimize in some cases with Ready Now, but a lot less on both of them. So hopefully that answers that. And it's not one or the other. We are working on faster and faster, and we are working on others too.
Yeah, but if you compare your throughput on batch mode with a hotspot, which one is faster, hotspot or as other?
If we compare, so the benchmarks we compare on, we're faster. The benchmarks they'll compare on, they'll be faster. And guess what? That's how benchmarks work, right? We just don't show you the bad ones, right? I don't think we do. We do run internally all kinds of benchmarks. To us, a benchmark is not an industry standard benchmark. We do use them. But it's a lot more important to us to take real-world workloads, real-world applications. So we try and get our hands on a lot. And some people here in this room have contributed some workloads we use on the lab to do that. So, for example, I focus a lot more on actual Cassandra behavior than on spec JVM 2008 and how quickly it inverts a matrix or does ray tracing. Right? I mean, and the fact that it's got a Monte Carlo simulation that has nothing to do with how you write Monte Carlo simulations. So if you want to make that code really run fast, you need to take code that is really badly written to do Monte Carlo and make it fast, which doesn't help anybody that actually runs Monte Carlo simulations because they don't write it that way. So we try to focus on real-world, actual customer, actual A/B tests, actual, prove that things work. And that's how we try and drive our focus in engineering in any one of these. If somebody somehow gets a big pause, we go work on it. If somebody has code where Falcon isn't fast or where it could be much faster, we work on that, and same for those. I will say that we have some very good examples of Falcon being much faster. So, for example, Cassandra throughput benchmarks, Zing is now about 8% faster at raw throughput than Hotspot on most of the workloads we run on. 8, 10, something around that level. And that's even though we're running a concurrent collector. So often we'll have the, where do I pay? Is it going to run slower? Well, we're 8% faster. Do we need to answer more? Now, could we run even faster if we didn't do a concurrent collector? Probably. But we're not willing to sacrifice that, right? There are cases where Hotspot is still faster than us, and we tend to work to close them really quickly, so that changes week by week or month by month. There are places where we have outrageously faster speeds. So for example, Neri has a whole bunch of micro benchmarks, really cool micro benchmarks. You know, remember micro benchmarks? So we are 40,000% faster than Hotspot on some of those micro benchmarks, which probably means we optimized the way a micro benchmark Hotspot didn't. Not that we're actually 40,000% faster at something, right? In some cases, Hotspot on a micro benchmark might be 30% faster than us too. That still happens here and there. But you know, we actually look at win rates and all that. I'd say we're at an 80-20 right now. Falcon is a good bet. It's not an always win, but if you're flipping a coin, Falcon's the better side to bet on. That's that simple, and not by 51%. You know. Anybody here have actual hands-on experience with Falcon? You do, yeah. Do you have anything to say about what you've seen?
Yes. Yes, we benchmarked Falcon compared to C2, Zing C2. And it's a little bit better, but on our application, the C2 from Hotspot is a little bit better, just because we are doing a lot of memory accesses, and the LVB from the C4 is we are paying this price. It's like 8% slower for Zing compared to Hotspot, but we have on a good side that we don't have any pauses, or the worst pauses that we measure is 2 milliseconds, but just on the benchmark, not on a real workload. So yes, we are trading like 8% of the raw performance, low latency, to have less
consistency,
no pauses that we can measure.
So I think that's a good real-world example of no, Falcon isn't faster than Hotspot for your workload. Hopefully over time that'll actually change in reverse. You can think of it as we've closed the gap, we want to flip the thing. And there are cases where, yeah, running C4 using 64-bit words instead of compressed oops, using our LVBs does accumulate to cost. And we keep working on making that better. But, you know, the Falcon is a step up from everything we've done before. Our actual investment in Falcon is not at a point in time. The reason we put 3 years into this is not because we wanted to get a little faster. It's because we wanted our velocity to grow. We estimate, based on actual building optimizations in Falcon, that we are roughly 2 to 3 times faster at building optimizations now than we were a year ago on this new platform compared to having done it on C2. And we believe that our speed and hotspots are similar on C2. So we've basically at a point where our optimizer writers get to write more optimizations per year, per month, per man year. And we're hoping to win based on that. If you actually look at future direction, it's pretty clear Oracle's also given up on C2. Right? They're investing in Growl. It's a new compiler that they're hoping to build better and faster optimizations with. C2 is 20 years old. It's served the community very, very well. But building new optimizations with it takes a long time, not because it's hard to build a new optimization. It's because of the 40 things that you didn't think of that optimization will break and then you have to go fix. And you know, with 20 years of that crud behind us, it gets very slow to release and build. So we've had several optimizations that we tried to do, and we just couldn't get to a stable product with. And in Falcon, it was easy, and we shipped them in weeks. So we think that's a trend. What that means is next year and next year and next year, we expect that to keep going and to keep going at a higher pace than what Hotspot can currently do with C2. When Growl actually comes out and actually becomes a production compiler, we'll see how we do compared to that. But I often get the, okay, why Falcon? Why don't you do Growl? Well, Falcon is production-worthy shipping right now for Java 7, for Java 8, and for Java 9 when it ships. Growl will someday be a production compiler either for Java 9 or Java 10. We just proved that we invested in the right compiler, right? Because I wouldn't have anything to ship if I was waiting for Growl still. But in a few years, I think we're going to be looking at actual competition on new JIT compilers, and that'll just be an interesting, good place to be, good for the community, right? It's good that people are doing things in competitive, different ways. So we like to talk about it that way because we think we're winning, but you know. Yeah. Okay. Other questions? Okay. Well, let's do the
one last question.
Let's do the last question and then we'll get up
first
and
of all,
get off the recording.
Thanks for the talk. It was really great. Yeah. Do you have any bench on big memory system, or do you still run on gigabytes JVM?
So Zing works just as well on a gigabyte as it does on 2 terabytes. We don't behave any differently between those two. That doesn't mean you need 2 terabytes, but if you need 2 terabytes, boy, do you like having Zing, okay? And we have people running 1.5 terabyte data sets and 2 terabyte JVMs and are really happy to not pause for 13 minutes every once in a while. We are right now working on growing from 2 terabytes to 4 terabytes and maybe to 8. We'll see in the future. So that's roughly the edge of where Zing works, which is a pretty wide range of the real world. The vast majority of actual use cases, though, are in the 6 to 20 gigabyte range, 6 to 30 gigabyte range. That's where, you know, because we run Cassandra, we run Solar, we run Elastic, we run a lot of things people don't even think is Java. They don't program it. They just run a database or a message system, or, you know, Kafka just doesn't pause for 3 seconds. That makes some people happy. And those things don't need, you know, hundreds of gigabytes of memory. They weren't built for it. In fact, if they were built for it, they probably wouldn't work well without us. So, you know. But in the places where you need it, yeah, Zing can go pretty high already.
I was thinking of the garbage collection because you always want to avoid garbage collection on big memory, and your guess is to garbage the more often you can. So isn't it opposite strategies? So when you're running a terabyte live set, we'll probably end up spending about 10, 20 minutes in an old gen. So we probably won't do it every 10 minutes, you know, because we can't. It takes 20 minutes. But when you use Zing, garbage collection is a background thing. You can limit how much effort it'll do by limiting the threads it'll use. And as long as that's happening, there's nothing negative about it running. It's a retraining of how you think about it. So the reason you try to not garbage collect a lot is because it hurts. What if it didn't hurt? You change how you do things. So that's why we can run them every 10 minutes. They don't hurt. And the trade-off is then you don't have rare things that only happen at high load at 3 p.m. Right? So you can test. You can actually experience the system the way it is. So with this, I think I'll take the mic off. We can chat and eat, and I'll keep chatting and answering questions. But for the recording and for this boom mic thing, we'll stop at this point. Thanks again.
Thank you.